Okay, this is by the way, this whole demo stage thing is new to this conference, and Ben and I are trying to make it not new next year, so it'll be regular next year. There's a huge range of stuff that we're doing, and this one is Stump the Energy Nerds. Well, I guess Martin Holladay. Martin, what's your affiliation? Fine Home Building?
And Green Building Advisor.
And Green Building Advisor. And I think Martin's a pretty familiar name, if not a familiar face, because he hides behind electrons a lot, right?
Right.
Yeah. And Bruce Coldham, I promised that if Martin, that if he were to sit up there, I would be down here and solicit questions, and I've invited one or two other energy nerds candidates for same to appear. So this is a light-hearted event, and does anybody have a question for Martin?
Anybody who's familiar with Jeopardy knows that it all depends on which categories they fall into. So if you want to stump me, it's sports, opera, and TV shows. In those three categories, I am useless. So, but if you don't want to stump me, I can maybe try on energy questions.
Okay. Do we have a question?
I was wondering about if you can use, I'm not very educated in this field, if you can use dense packed cellulose for air, to block air infiltration somewhat.
Well, that's a good question. Dense packed cellulose definitely reduces air leakage in homes, and weatherization contractors know that if you do a blower-door test before you insulate an old house with dense packed cellulose and after, you'll get a very noticeable decrease in air leakage. But dense packed cellulose is not an air barrier because you still get airflow through it. Not quite, so it's far better than fiberglass bats, but it's still not quite an air barrier. And if you really want an airtight house, or a house, I should say, that gets close to passive house standards of airtightness, you will still need an air barrier in addition to dense packed cellulose.
And what we find with dense packed cellulose is that if your air barrier is on the outside, it is very useful to stop the interior air from simply washing through the cavity and coming in contact with that cold outer surface, which is still inside the air barrier, but which is cold. So the dense pack forms a very efficient prevention of air washing through the cavity. So that's another function, I would say.
For instance, you would recommend to seal around electrical boxes, even if you do dense packed cellulose in general?
Well, there's less of a need to worry about air leakage around electrical boxes. It really comes down to what your air tightness goal is. I think many people are satisfied with not going to airtight electrical boxes with dense packed cellulose, but like I say, if you're aiming for passive house, you're going to want to seal everything, and you're going to want airtight electrical boxes as well.
If your electrical boxes are inside the air barrier, though.
There you go. If you have a service cavity on the inside of your insulation, or if you do an airtight barrier at your sheathing level, which a lot of people do, like Mark Rosenbaum, you tape between your OSB or plywood sheets, and there your air barrier is airtight on the outside, then it really doesn't matter what you do to your electrical boxes.
That's when you're taping the electrical feed from the power outside into the service panel and around the exterior outlets, but there's precious few penetrations on account of the electrical system if you do it the way he just mentioned.
So if you have on the outside of your wall, if you have your moisture barrier and an air barrier and then your sheathing, how do you cover up the bottom of that from moisture getting up through capillary action or just air getting up there? How do you seal the bottom?
Are you worried about the air gap, the bottom of the rain screen gap, or where are you worried about capillary moisture from the concrete foundation? Where are you worried about the source of the moisture?
Just from the outdoors, how, like, because the wall, the outside of the wall on the outside of the frame is probably going to hang off the floor of the building, I would assume. So
right.
How do you seal? What way would you recommend going about sealing the bottom of the wall?
The most important thing is all wooden components of your house should be at least 8 inches above grade, and 12 inches is even better. So that's step one. If you're well above grade, that helps. If you have rigid foam, that is outside of your sheathing. That is usually sealed along the bottom, either with a wood strip or with metal flashing. If you have a break on the side, you bend up some metal flashing to cover that foam. And if you have an air gap between your foam or between your sheathing and your siding, a rain screen gap, then usually you have insect screening that's folded under and around, or Coravent type product that fills that. Now, I'm not quite sure if you're worried about rain splashback or humid air.
Just dirt and everything in general, protecting it from the elements, because I know it's open.
Keep it above grade is the basic thing. And a lot of houses, especially handicapped accessible houses, have a problem because you want, on-grade access, or you want a 1 in 12 ramp to get to the front door, and so they try to minimize that height, and then you run into a conflict where you really have wooden components way too close to grade, and I've seen that a lot on houses built in the 80s and 90s. You get a lot of splashback. So, the old-fashioned way is an elegant house is 18 inches above grade, and it has a nice grand front entrance. That works. It's far more durable. When it comes to handicapped accessibility, you often have to make a compromise, or you have to have a ramp, in my view.
Hi, Martin. Bruce Friedman, Gallagher Home Builders. I was in this seminar before with you where they were talking about health issues and ventilation, and so it brought up my concern about ventilation and projects that I've done in the past, which we really haven't addressed that quite or at all. So what should I do as a builder now going forward about ventilation, and what's your take on how we should actually be ventilating structures, not a passive house, but maybe beyond standard construction, airtight houses. So what should we be doing?
Well, I think these days, if you're paying attention to airtightness, at a minimum, kind of to protect yourself as a builder, you have to comply with ASHRAE 62.2. Even though that's that's not yet code, or not yet a requirement, as far as I know, in almost everywhere in the U.S. ASHRAE 62.2 is the residential ventilation standard created by the American Society of Heating and Air Conditioning Engineers, and it's been around for probably about 10 years, and it requires a certain amount of CFM per square foot of occupiable space, plus a certain number of CFM per person, which is usually each bedroom plus one. And for a 2,000 square foot house with 3 applicants, I think it's somewhere in the range of 40 to 56 or 60 CFM for most average single family homes. That's the range. So it's not a high ventilation rate. It can be provided 24 hours a day, or it can be provided intermittently as long as it adds up over 24 hours to the ASHRAE 62.2 rate. It can be done with exhaust-only ventilation, with supply-only ventilation, or with an HRV or ERV. ERV. All of those are acceptable under ASHRAE 62.2. The least expensive way to go, especially in New England, is exhaust-only ventilation using a high-quality, usually Panasonic exhaust fan in the bathroom on a timer. And if you have a forced air system, a lot of people use what they call central fan integrated supply ventilation, which is a duct from the outside into your return air plenum, which is controlled by a motorized damper, and an air cycler control, which turns the motorized damper on or off so you don't overventilate or underventilate. And that control also energizes the air handler fan to ventilate periodically during the swing seasons when your air conditioner and heater are not working. Sounds more complicated than it is, but that's a real quick summary.
How is that damper controlled? Is it through your thermostat? Or?
The damper is controlled by a patented device called the air cycler, also sold as the fan cycler. It's available from several manufacturers. You can Google fan cycler or air cycler, one word, and you'll find it. And I don't know what it costs. I think it's less than $100, but I haven't bought one. It's a little electronic gizmo that attaches somewhere near the motorized damper or the furnace. You wire it both to the motorized damper and the furnace controls, and the instructions come with it.
Hi, Martin. I'm working on a rehab in Troy, New York. It's a simple brick building, and it's totally gutted, so it's just a brick box from 1860. I've got a lot of people recommending closed-cell spray foam for moisture issues. I'm wondering if there's any foam-free solutions to insulate and air seal the house that you'd recommend.
I assume you're talking about a multi-wythe brick building with structural brick. I've got an article on that topic that you can read on the Green Building Advisor website. And a lot of work has been done on this issue by the Building Science Corporation, and they have some good articles. there are a lot of caveats, and Chris Benedict is an architect in New York who works with Henry Gifford, and she has insulated many existing brick buildings, the kind you describe, with dense packed cellulose. I consider that an experimental method. As far as I know, she hasn't had moisture issues. The standard recommendation is closed cell spray foam directly against the interior of the brick as safer because it has no ability to absorb moisture. The risk, there are 2 or 3 risks to any type of insulation on an old brick building. The first risk is moisture damage due to increased freeze thaw, because you no longer are driving heat through the bricks. The bricks now become colder, therefore wetter. And you cannot do any insulation without being sure that you've done complete moisture management on the outside of your building. So rain is deflected, the flashings are perfect, the roof overhangs are extended. If you get a lot of rain on your building, you're at risk. If you're in a cold climate, you're at risk. Did you say Troy, New York? You're at risk in a much more dangerous situation than someone in Philadelphia. And so you can't put too much insulation. And then the second factor is beam pockets. If you have any wooden beams or joists that sit within the brick, they will rot eventually because they'll be cold and therefore wet. And so there are various ways to address that, including leaving insulation away from the beam pockets and just having an energy penalty. People have experimented with other tricks that seem a little goofy to me, but it is a concern. Then there's the chainsaw method, where you simply chainsaw off the beams and you support them on an independent post inside of your insulation. I think the chainsaw method is probably the best way to approach beam pockets in an insulated brick building. All of those caveats introduced judgment calls. And the quality of the brick is one issue. You could have freeze-thaw damage in some types of brick, and a harder, better fired brick will not have freeze-thaw damage. So you have to kind of test the brick in some cases or risk it. So there's no easy answer, and hire John Straub if you really want to know, and for a few $1,000s, he'll come to your place and run some tests on your brick, and then you'll sleep better at night.
I floated this on the GBA a couple of weeks ago. If I'm doing a duct penetration where cold air is going to come into the duct, for instance, for an HRV input, what's the best way to seal that up through the wall so I don't get condensation on the inside where the duct comes in? Because that whole thing is going to run cold.
And you've got PVC at the moment.
Yeah.
Right.
Let's not go there.
No, but it turns out, I went back and reread an article that Dave Hansen and I wrote for JLC, and Dave Hansen uses PVC as well. So I guess short lengths of PVC, you're not the first one to use PVC for fresh air ducts. It makes me a little nervous, but evidently you're in good company.
It's white Scad 40. It's not going to leak
But,
anything.
you know, what you said on GBA is you pulled away the insulation and you sealed it, and it seems to be doing fine. So have you solved your own problem or not?
So far, I'm waiting for warm weather to really rip it apart
Right.
and redo it. But I'm just wondering what the best way to go at it in general is, especially if it was a metal duct and not PVC.
I mean, if I were doing it and really, I mean, it's a good question. And the question is, the cold air intake for a HRV comes through usually a rim joist, an insulated rim joist, or a wall. And if it's a metal duct, there's a thermal bridge. And there's a potential for condensation because the air coming in will occasionally be 0 degrees Fahrenheit. So you're bringing 0 degree Fahrenheit air through your wall, and you can dampen adjacent wooden components because the condensation forms and wicks into the wood. So what's the solution? I mean, the obvious solution is some type of insulated duct. So you can either rig up your own insulated duct, or you can put insulated flex duct through there. I imagine insulated flex duct would probably work. I also imagine rigid duct with a foam box around it, or a sprayed in place foam around.
Yeah, that's the way I do it.
The duct would work. And, you know, I've never done it, so I don't think any of those solutions would lead to a problem.
The reason I favor that spray foam around an oversized hole where you're actually filling the annulus essentially with the spray foam is that we very frequently these days use the exterior sheathing taped as the air barrier, so it's essentially the band joist could become part of the air barrier if the sheathing is sealed to it, so it's all part of the air barrier seal. And it also, if you use that technique, you would have an insulative component to the air sealing as well.
You're making a buffer around the entire duct so that the whole thing floats in its own little cold universe and everything outside of that layer is warm.
Bruce, I'm curious, do you use an actual duct within a duct?
No.
No, you don't. You just do spray the foam around the duct.
Yes.
Okay.
I mean, it's.
But if you
I
wanted to
don't-
make
I
it
don't
look
do
slick, you
I-
could get a
of course, somebody else
10-inch
could do it.
duct and run a 4 or 6-inch duct inside, and you could just spray foam between the donut.
Yeah.
There's a lot less condensation on plastic pipe than metal, too.
That's true.
That's why David Hansen uses it.
The last 5 to 10 years in New York City, there's been hundreds of, I believe you call it the EFIS, 1 or 2 inch styrofoam on brick buildings. I mean, they call it the Mediterranean of New York, and it's got the adhesive, the styrofoam, and then the mesh and stucco over it. I was really skeptical, and after looking at the buildings for years, they seem to be holding up well. I'm just wondering if that styrofoam over the brick on the outside solves the moisture problems.
Why can't you use EIFS to insulate an old brick building was the question, which is a rigid foam on the exterior covered by synthetic stucco. You are absolutely right. That is by far the best way to insulate an existing brick building. It's, as John Straub says, the right way to insulate an old brick building is on the outside. The dumb way is on the inside, but historical preservationists won't let us do it the smart way, so we have to do it the dumb way. You will have zero problems with the exterior insulation solution, except it'll look different. And the EIFS is a great, great system for old buildings, except right near the sidewalk where people kick it or drive their cars into it.
While we're waiting, I'll jump one in. We used to use solar thermal panels a lot, and recently, of course, PV has become quite popular, quite affordable, and quite well subsidized. But the question is, should we still use solar thermal panels with our low energy houses, or is it a better idea just to buy a water heater and buy enough more PV to power the water heater? What's the intelligent way to go about it?
Well, I wrote a blog on this topic a few months ago, and I couldn't really make the math work in favor of solar thermal. And I really think that PV is the way to go, and the PV prices since then just continue to drop. And the basic reason why solar thermal appears on paper to be better than it is because people pencil out the maximum potential BTUs per year that these thermal panels produce, but they don't take account for the fact that the demand and supply are out of balance, in time. And so if you have a hot period of weather in the summer, you can make tremendous amounts of hot water, but the family living in the house may not need very much hot water. They may be on vacation, or they may be at the beach, or they may just take fewer showers. And then in December, when they really are feeling chilly and they come in from a day snowshoeing and skiing and they want 12 long baths, there's no hot water. So you're wasting your summer hot water, and you're not having it when you need it. The advantage of the PV, of course, is if you're grid connected, every single watt you produce is credited to your account, and you never waste any of it. And you can do the math yourself. I do some calculations on that blog. The blog was called "Solar Thermal is Dead," and you just get more bang for your buck with PV these days. And I never thought I would live to tell the tale that way, because we're all brought up with the opposite assumption that solar thermal is far cheaper and more productive than photovoltaics. But it's a new reality out there. PV is cheap. And that applies, by the way, whether it's electric resistance hot water or heat pump hot water. And if you have a good place in your home for a heat pump water heater, which means if you live in Florida in your garage, or if you live in New England, if you have a really big, too warm basement, then the economics get even better.
They do. And the fact that you've only got one system that you're maintaining instead of two is another consideration sometimes, I guess.
Right.
Got a question?
So I'm wondering if there's any sort of threshold to make an argument for an HRV. For instance, if you're remodeling, doing a blower-door test, if there's some number, whether it's CFM 50 or whatever it is, where you can say, above this number doesn't make sense, below this number it makes sense.
That's a very controversial topic right now. I guess what did it used to be? Now, the advantage of being an editor who usually works in a home office is I can Google and look everything up before I come up with but was it 0.35 air changes per hour? Is that the old ASHRAE guide before ASHRAE 62? Yes, I'm getting some nodded heads, so I'm remembering correctly. So, you can do some back of the envelope natural air changes per hour guesses. And the natural air changes per hour based on a blower door result of 50 pascals depressurization is basically a guess. You're taking a depressurization number that occurs under blower door depressurization and trying to extrapolate what that means based on stack effect and wind. So you'll get a lot more air exchanges during winter when stack effect is forceful and a lot less during spring and fall, especially when the day isn't windy. So it's really hard to say. But the bottom line is, I think the way to decide whether you need mechanical ventilation is common sense, not a number. And that means in winter, do you have condensation at the bottoms of your windows, enough to be noticeable? Do your bedrooms stink? And do you notice a funny smell when you walk in after you've been outdoors for a while? And I think those are as good a method of deciding if you need mechanical ventilation as an actual number. The trouble is when you come up with a number, especially if it's applied across the board to weatherization programs, is we end up installing expensive equipment that might increase the cost of weatherizing low-income homes by a huge factor without having proven that these homes really need them. There's so many factors. Do the people smoke? How many people live in the house? What are their hobbies? How often do they cook? That it's really hard to just come up with a rule of thumb.
So if you don't have that ideal basement to put a heat pump hot water heater in, and you're building a little slab on grade house, what would you choose for your heating and or hot water system?
Where's the house?
Vermont.
The house is in Vermont.
And it's, good
and the house has
orientation, good, it's
does the house have access to natural gas?
No.
The house has
no
access to natural gas, and the house is in Vermont. And you're asking for what is a heating system and what is a hot water system? Mm-hmm. Good question. I think even in Vermont, if you're building a super insulated, brand new airtight house, or as close to airtight as you can get it, I would be tempted to use ductless mini splits. They are being successfully used in Vermont. Depends on how the layout of your house. If it's an ideal compact house that's not stretched out with a bunch of silly L's and bonus rooms, you can get away even with a single point source ductless mini split in the living room. That will provide you bedrooms that are 5 to 10 degrees colder when you close the door. And some people like it and some people don't. So it kind of depends on what you expect in your bedrooms. If you don't want that, then there's a lot of questions. Do you have a wood stove? Do you have a pellet stove? Do you want to have a wood stove? Do you want to have a pellet stove? So, ultimately, almost any heat source will work, and you just want to bring your BTU calculated heating load down so low that it hardly matters what you use. So, I don't even have a problem with a propane furnace or a propane boiler if you have a small enough house that it doesn't get used much. And sometimes it's good to have a heating system that can be serviced locally by somebody who can be called when your heat's off in January, and rather than getting exotic. I think that we're headed towards a future without fossil fuels, where we're going to be generating most of our electricity from utility scale wind and solar, plus perhaps biomass. So the idea of the all-electric house, I think, is the future. To me, that means there's nothing wrong with an electric resistance water heater, especially if you have PV on your roof and you do everything you can to minimize your hot water usage, including installing a drain water heat recovery device, which unfortunately won't work because you've got a house on a slab. So you might want to put a basement in there. In Vermont, a basement is useful.
Couldn't agree more. I was listening this time, so I'll say. The critical piece that I picked up from that is dropping your load down to the point where those heat pump space heaters work well. And the point source idea is a great one if it's a small house, because even though the bedrooms may be 10 degrees cooler, that's if you keep the door shut and so forth, that's in the coldest fraction of the year, so you figure out how many hours of the year you're working with, and you could say, well, I'll put a baseboard resistance heat or a ceiling resistance heater there, and if you're running it for 60 hours, the penalty is inconsequential, and you save yourself the angst of whether or not I can really go with this point source heater, because that's the way to go, I think. Couldn't agree more.
A little late coming in here. I just heard a few minutes here, but flat panel solar panels on the roof. I have a 120-gallon hot water tank in the basement. What is a good alternate storage solution other than just water? When I'm looking for energy density in a small storage unit.
You have solar thermal hot water panels on your roof?
Yes.
I think it's water. I don't think anybody's got anything better than water. I mean, you can add antifreeze to it if you're worried about freezing.
No, I'm adding for energy density. I'm thinking, do you have
Like
rock?
phase change materials? I'm not sure what you're talking about.
Well, you could go into rock. I don't know. Is there anything better than water?
I think water is cheap and widely available and has been used for that purpose for a long time. I mean, frankly, I think attempts to store thermal energy, usually in water or rocks was what we used to use for the hot air systems of the 1970s and 80s. I think it's foolish. I think there's a lot of reasons why we don't really need to be storing thermal energy for more than one day or maybe 3 days. So these ideas that I'll get a big flywheel effect and I'll put a swimming pool in my basement, which a lot of people have tried, I don't think the financial investment in these big tanks and solar thermal panels are ever pay back. I think what you want is a good thermal envelope and a really low load and make the energy when you need it. So it's hard to make the economics work on storing BTUs in water or rocks. But if you're doing it, I think water's the way to go. Bruce, you got an opinion on that?
I agree. They didn't call it the heroic age of solar for nothing. and it's a nice time, but it's the past. It's not the future. Okay, I said something.
Yes, but you're assuming that my house is an ultra-high efficiency thermal envelope instead of an 1888 house balloon framed with, unless I start tearing siding off and insulating, going nuts on insulating.
Well, that's a good point. And then if you want to put panels on your roof and you have some area that faces south, go PV. I mean, that's going to drop your energy bill more than anything else. You'll get credit for every single watt that's produced. And you'll never have a plumbing leak. You'll never have a pump failure. You'll never have a burst tank in a wet basement, all of which happen all the time with solar thermal.
Yes, I was just wondering, just what is your feeling on HRVs or ERVs? Do you, zone 5, for instance? I
think that a fully ducted HRV or ERV system is the best possible ventilation system. And if you if you want even distribution of fresh air throughout your house at the lowest possible operating cost, they can't be beat. There's only one downside, really, besides, I guess, possible repair costs, and that is the cost of installing them. I mean, if you've got the $2,000 that it takes to install a good system, and sometimes $3,000 to $5,000 in some homes, there's absolutely no downsides. They recover their energy, they put the fresh air exactly where you want it, they take the exhaust exactly from where you want it. I think in a lot of homes, especially smaller homes, it's hard to make the economics work if you compare it to an exhaust-only system. You're never going to pay back the incremental cost in the energy savings in most climates. Well, in Vermont and southern Canada, actually, you do begin to pay back. But certainly Boston South, you don't pay back in energy savings the incremental cost. And there's been some good studies on that. But you do get a better system. And a lot of people say, I don't care that it costs a few $1,000s extra. I want a good ventilation system. So that's the story.
Sorry, could you just clarify the difference between an HRV and an ERV?
Sure. HRV stands for heat recovery ventilator, and it includes a heat exchange core whereby the heat from the exhaust air in winter is transferred to the incoming supply air without any air mixing. So, some types of plates or small tubes that get near each other and the heat it goes from one airstream to the other. An ERV has a core that transfers both a portion of the moisture in one airstream and the heat. And it's usually a porous material or some type of paper or plastic that allows a little bit of moisture exchange. The idea is if you have very dry indoor air that's been air conditioned in a hot climate, you've paid to dehumidify that air, you hate to bring in a lot of humid air, fresh air in the summertime to ventilate your house. So by transferring some of the humidity in the incoming air in summertime into the exhaust air, which is dry, you're therefore dehumidifying to some extent the incoming supply ventilation air, and vice versa. You get a slight humidification in winter when the indoor air may be too dry. There are some downsides to ERVs. You do get a little bit of gas exchange. So if there's formaldehyde in one airstream, it's also transferred to the other, and Max Sherman raised that question. I think that's kind of a red herring because you're still ventilating your house, you're still diluting everything. And some people don't really want to humidify their air in winter. They really do want the dehumidifying effect of that really cold, fresh outdoor air. And they have an indoor environment which is too humid. So HRVs make more sense. So the other thing to think about is, although they make a slight difference, I think the difference is exaggerated by the manufacturers. And in most cases, you're not going to notice the difference either in your energy bills or in the indoor environment. So it's either one can work well in most climates.
I want to thank you all very much for coming and for your participation. I think this was a great success. Thank you all.